recording the talk now? Okay. Now I get it. Okay. Because it always tells me. So, okay. I I wanted to talk about the James Webb Star Destroyer, but uh, I guess I was convinced into talking about the James Webb Space Telescope instead. It's just kind of interestingly peculiar since it hasn't done anything yet, but we'll get around to that. And so I'm going to talk about James Webb Space Telescope instead, named after James Webb, second NASA administrator. He's the guy who did Mercury and Gemini and the run up to Apollo, because Apollo 11 was in 69, remember, so the pre-Apollo 11 missions, a lot of them were under him. And so, the Hubble Space Telescope went up, launched in 1990. In about 1996, people started making plans for the next generation space telescope. And in 2002, they named it James Webb Space Telescope. And then just a few months ago, there was some agitation to change the name again because it seems James Webb had some social ideas that, shall we say, are unacceptable today. And may have done things in somebody's minds that weren't all that. So you should change the name, but NASA says, no, they're not going to change the name. It's going to be James Webb Space Telescope. Well, so, okay, it was originally scheduled for launch, and I can't read when because the Zoom heads are covering up part of my slide, but you can read the year. I can't. For a total cost of $500 million. But it's been delayed 16 times. Now it's scheduled for launch on December 18th at a cost of slightly under $10 billion. The last government accounting office report said $9.7 billion, but that could easily become $10 billion by the time they launch. Who knows? The way they count their numbers. And so there's a picture of it down here, and we'll go into it in considerable more detail. There's the 6.6 meter primary mirror and the spacecraft. And you notice all the pictures will show you a pink bottom, and it actually does look pink, and you'll see, and I'll explain why in a few minutes. So it hasn't launched yet, but it is going to launch on the 18th on an Ariane 5. So here's an image from January 2020 of a communications satellite payload being launched from French Guiana on an Ariane 5. So when it does launch, it will probably look like this. This is the same rocket it's going to launch on. I don't know if it's the same launch pad that it's going to launch from, but this is the same rocket. So I haven't been asked to give a talk before on a space telescope that hasn't even launched yet. So you'll have to do without most of the pretty pictures and things you see from space telescopes since it hasn't done anything, but I'll try to put in something reasonably interesting. So the Webb is kind of publicly sold PR-wise as a follow-up to the Hubble Space Telescope, or maybe a replacement, because we can't really service the Hubble anymore, not easily anyway. And I don't think the current Dragon space capsule is designed in a way that would really allow you to do that. And so without being serviceable, the Hubble Space Telescope eventually, like by 2030 or 35 or something, will be in danger of maybe plunging into Earth's atmosphere because of friction with the upper atmosphere where it is. So we may lose the Hubble at some time in the next decade or two. But really, the Webb telescope is a follow-on to Hubble and Spitzer. The three of them combine really to make an interesting triad of space telescopes. Hubble, with its 2.4 meter mirror, slightly smaller than the 100-inch at Mount Wilson, is aluminum-coated ultra-low expansion glass. But both Spitzer and Webb are gold-coated, and the mirror is made of beryllium, which is a fairly soft metal. but has outstanding thermal characteristics. So it expands and contracts due to temperature even less than the ultra expansion glass. It's the ideal stuff to make one out of. And so here, this shows the wavelength ranges that the telescopes will be using. Well, now Hubble Space Telescope, since it is serviceable, its capabilities have changed as people have gone up, swapped out old instruments, swapped in new instruments. So what I put here is the full range of wavelengths it has operated over, 0.1 to 2.5 microns. NICMOS instrument's not there anymore, so I don't think it can reach out this far anymore, but it could. It did imaging at 2.5 microns. This has a fairly large mirror, but it was intended to concentrate mostly on the visible spectrum, visible light. But it can see some of the near ultraviolet. About 0.3 microns is something like the bottom end of human vision. They'll go down to 0.1, but about 0.65, 0.7 microns is about as far as humans can see. It's much farther into the near infrared. The Spitzer Space Telescope took up where Hubble left off with the short wavelength IRAC instrument, giving you 3.6 to 8 micron imaging in 4 channels. And when it ran out of cryogen, it could use the bottom 2 wavelengths, 3.6 and 4.5, and nothing else. But when it had its liquid helium coolant, it could go out to 160 microns imaging, and it did spectroscopy from 5.2 to 38 microns. So James Webb is in between. It has, of course, a much bigger mirror. Its longest wavelength is 28 microns. So Spitzer could do spectroscopy farther out than James Webb, but with a very much smaller mirror. So even though the Webb telescope won't look as far in wavelength, it can see much dimmer things because it has so much bigger mirror. But James Webb has has very little visible light capability. Its shortest wavelength is 0.6 microns, which is a little bit blue of hydrogen alpha, and around 0.7 is the red limit of human vision, and about 0.5 is the middle of human vision. So this is really from the red end of visible. It doesn't do a lot of visible in the infrared, and does imaging and spectroscopy throughout this entire wavelength range. But it's the size of the mirror that's the real discriminant here. And they give the relative areas of the mirrors, 4.5 and 0.6 square meters, look good for Hubble and Spitzer. I haven't been able to figure out where 25 square meters came from for James Webb, because whenever I try to figure out the area of the combined hexagons, I get about 35 square meters. So I don't know what I'm doing wrong, but this looks like a fishy number to me. So here it is. Now you can see what the mirror looks like deployed on this model down in the corner that it shows you the mirror all spread out. But here in the picture, it's packed up for shipping and launch, at least the first stage of packing up. So you can see that the secondary mirror, which would normally stick out like it does in the bottom picture, is pulled up and folded over. The 2 wings of the primary mirror are folded back. And all this stuff, of course, has to unfold in flight. And we'll look into that in a little more detail in a few minutes. But every other space telescope that's gone up so far has had a smaller mirror and has gone up as a single piece. This is the first time the mirror has had to be foldable, basically. And the whole telescope it's the most complicated thing I've ever seen anybody try to launch. It's just going to unfold. It's ridiculous. But we hope that it works. So here I'm just looking at one of the hexagons. Of course, you don't need adaptive optics in space because there's no atmosphere to worry about, but you can't go service it, and you really can't control it from the ground like if you have your own telescope, you can move mirror segments around on the ground like the Keck telescopes or something in real time. You don't have any way to do that with the space telescope, since you're not like looking through it in the same way. So there's a network of actuators on the back. There is a piston in the middle that pulls up and down that will change the shape of the hexagon. And likewise, these actuators, there are 3 sets here, will squeeze or pull here. And that also, so they have multiple degrees of freedom for moving a hexagon just straight back and forth like this, or stressing it to change its shape to get all the hexagons working together as a regular mirror. So once it's actually working, the first thing they'll have to do is do that. They'll have to massage all the hexagons of the primary mirror and get them into working together. And they're fairly light. If you each segment weighs about 46 pounds, and if you fully assemble everything, put all the actuators and all on the back, it's about double that. So you're looking at like 90 pounds, something less than 100 pounds. So even here on the ground, somebody can kind of pick up one, and a couple of guys can pick one up and haul it around. They're not that heavy. There's 18 segments, and the only number that I've seen that is consistent across the James Webb Space Telescope web pages is that they are 1.32 meters flat to flat across. Throughout the James Webb web pages, they quote the surface area of the mirror as being 6.4, 6.5, or 6.6 square meters on different web pages. So one assumes that the James Webb Project people do not actually know the area of their primary mirror, since they can't seem to put the same number on 2 web pages. But if you believe that 1.32 meters, then it's 6.6 is the correct number from flat to flat across the mirror. The optical configuration is a peculiar 3-mirror anastigmat to get rid of distortions from the optics. And so it looks like a Cassegrain with the primary mirror and the secondary mirror. And so the light, comes in as usual, comes out to the secondary, but the Cassegrain focus is in front of the primary instead of behind it, like going through the hole the way you normally expect. And so the light passes through the Cassegrain focus. It's an off-axis tertiary mirror that bounces the light off of a fine steering mirror. And this mirror's job is to compensate for jitter or random motions of the telescope. And then it goes from there into the instrument package. So it's about an F20 with an effective focal length of 131.4 meters. And on this page, they do give 6.6 meters as the circumscribed circle. And that is indeed what you get if the hexagons are 1.32 meters across. So this is a peculiar. George needs to mute his iPhone.
Oh, sorry.
Thank you.
My apologies. Sorry.
So I haven't seen this optical configuration on any other space telescope or big telescope on the ground, but I guess it's, optics people, telescope people must know about this. I don't. So what do I know about optics? So if there are telescope people listening, you probably have heard of this before. So this is the sun shield, which is really a pretty impressive device. So it's called a 5-layer V-groove radiator design. Its size and shape is intended to limit a momentum transfer from the solar radiation. That's not something you ever have to worry about on the ground, but when you're in space, the sunlight will torque your spacecraft. And eventually you need to worry about that. And you have reaction wheels and reaction motors to dump angular momentum the spacecraft picks up. But then in this case, if you put up a big sun shield that's got a big surface area, you're going to get a lot of solar radiation pressure, and you need to worry about it. And so they've designed this to minimize that, but they have reaction wheels and steering motors to bleed off the angular momentum they get from sunlight occasionally. It's a Kapton thin film. Both sides of all 5 layers are aluminized, and the bottom 2 layers here are have a silicon doping added to the aluminum, and it's the silicon that looks pink. So in all the photographs and artistic images of James Webb, it has a pink bottom because that's what it looks like. It looks pink because of the silicon. So it's fairly large, and nearly 70 by 46 feet. And the sun-facing layer is quite thin, 0.05 of a millimeter, but the other layers are even thinner. They're 0.025 millimeters. So it's Kapton, so it's fairly high strength, but very thin. And you can see how big it is from the crowd of people standing around it. And the result is the cold side of the spacecraft is down around 38 kelvins, while the warm side is around 398 kelvins, assuming that the sun shield works the way it's supposed to. So here you see the spacecraft on the right, the pink bottom, where all the computers and command and control stuff and communication stuff is down at the bottom on the sunlit side. There are solar panels also on the sunlit side, so it's solar powered. But up on the cold side, in this image on the left, you can see the primary mirror, and over on the right, this black monolith behind the mirror is where all the instruments are, all the imaging and spectroscopy instruments up in the cold where you want them, because you don't want to see the temperature of the telescope, you want to see the temperature of the thing you're looking at. And this, of course, raises the question, how does this shield do this? Because this is really pretty impressive. It doesn't look all that big, but you can see here, compared to these maybe 6-foot people, that's about how big this looks, maybe a little bit bigger, to cut off that much heat. And so the way it works is, and the reason why both sides of each layer are aluminized, when the sunlight comes up and hits the bottom layer, it bounces off, most of it. Some of it gets through, as will always happen, but the next layer up is also aluminized, as is the back side. So that radiation, thermal or non-thermal, tends to bounce back and forth and come out through these sides. But some of that will get through, and so the next one is also aluminized, and the same thing happens. So you get this through 4 layers. By the time you get to the top, you have maybe 200 kilowatts of solar energy hitting the bottom of the sun shield, and you have about 1 watt coming out the top, which is how you are able to maintain 38 kelvin instead of 398 kelvins. So it's a pretty clever design. I assume it's been tested down here on the Earth. I didn't see a documentation for it, but then I didn't read every document that they have available. So I assume they've tested this in their in Space Environment Test Center, but we'll find out how good it really works out there in space. But it's a pretty ingenious design, if you ask me, but it has to unfold, and we'll talk about that in a few minutes. So here's what the layout of instrumentation looks for. Of course, the primary mirror and the science package, the spacecraft bus and the high gain antenna. There are star trackers that allow you to orient the spacecraft. The star trackers know what stars they're looking at. They know what the sky looks like. So if they can identify the stars, then they know how the spacecraft is oriented. it's the same kind of thing that your new GPS enabled telescopes. They know what time it is, they know where you are, they know what the sky looks like. So they don't even need to identify a star. They can just look and see the patterns and know, okay, I know where I am now. And then they can point to whatever you want to point to. And there is a momentum. This thing back here is a momentum adjusting panel. So you can move this up and down like a flap, and that will change the angular momentum of the spacecraft by redistributing its mass, and that'll give you an opportunity to not have to fire reaction jets or use your jet fuel. And here's the solar panels on the front side. They're kind of over here where you can't see them well. So there's the solar panels. And there, of course, is the spacecraft looking from the side, same image that you saw before. Now here's the whole thing being packed up. And here you can see the pink color on the bottom side of the Kapton sun shield. It's all multiply folded up and packed in a pretty complicated array. And so when it's folded up, it looks like the image on the left here, where the mirror is folded back, the sun shield is wrapped up and then folded up so that everything can fit inside the Ariane 5 when they launch it. And of course, this all has to unfold, and there's a zillion steps to unfolding, and every one of them is basically critical. If one doesn't work, then the whole thing is junk for $10 billion. So there's a high priority to making sure that this works. So it has been shake tested. They put it into the space flight simulator and bounced it around and hit it with the low frequency sounds that you expect, high power sounds when you launch, to make sure you don't shake up any of the rotating motors and levers and the like. And so far it's passed those tests. So we like to hope that in space they will perform better than the Galileo antenna did, which, as you may recall, did not deploy properly, and they had to completely rework the way they get data from the spacecraft. And it was they were able to get around that, and it was successful. I don't think you can get around most of this if it doesn't work, because you need the sun shield, or you can't observe at the infrared. And if the sun shield won't get out of the way, you can't deploy the mirror. There are lots of things that can go wrong. And so this image gives you the high points where the fairing separation has to separate from the launch vehicle, solar array deployment. The sun shield has to deploy fore and aft and off to the sides. There's a tower that has to deploy. Primary mirror assembly has to deploy, and the backplane assembly. This is just a few steps. They have a movie that shows how all this happens in excruciating detail, but I can only find it on YouTube. So I have a link, and what I'm going to try to do at the end of my talk is play the YouTube video, which lasts about 5 minutes, which goes through all the details of everything that has to happen in the unfolding and unpacking sequence on its way to the Lagrange 2 point. So you can appreciate how complicated it really is. And since I know last month you had your talk on Lagrange points, I'm not going to go into any detail as to what's going on there, since you are supposed to remember that and I'll already have a pretty good idea what's going on. Suffice to say that the L2 point is a point where the Earth, Moon, Sun gravity pretty much is balanced. It's not a real stable equilibrium. You can't sit there at that point, but you can orbit around it. And if you have some station keeping thrusters, you can stay there relative to Earth. So it's about 1 million miles out. And so the spacecraft will orbit around the Lagrange 2 point in a stable configuration. That's where the Planck cosmic microwave background mission was. That's where the Herschel mission was. And there must have been other spacecraft that have gone out there. I just can't remember at the moment. So it hasn't done anything yet, but we can take a look at the capabilities of the instruments that it's going to use. And this is an overview. You have four basically instruments: the near-infrared camera and the near-infrared spectrometer. And I forget what the FGS stands for, but we're going to see it in a minute. And the mid-infrared. And so the short wavelength instruments are mercury, cadmium, telluride detectors, and the long wavelength is an arsenic doped silicon detector. There's quite a bit of capability here in this 0.6 to 5 micron capability, and NIRCam has spectroscopy and imaging in two separate bands from 0.6 to 2.5 and 0.6 to 5. Only MIRI goes out to the real long wavelengths beyond about 5 microns. It's only one instrument. And so these instruments are imaging, spectroscopy, coronagraphic imaging, and MIRI just goes mostly spectroscopy and out onto the long wavelengths. So for the near infrared camera, it does direct imaging from 0.6 to 2.3 and 2.4 to 5 microns. And what I plotted here, this plot comes from the James Webb Space Telescope web pages, are the channel filter shapes, basically. So you see wavelength in microns along the bottom and the throughput on the top, and like what percent of the light gets through, maybe 40%, 20%. It's not normalized the way you would normally do. And so this shows you what the shape and sensitivity of the bands and how wide they are in wavelength. So you have a pretty good spread of wavelength. I'm not sure why these are narrow band. If this is this is spectroscopy down here, 2.4 to 5. I'm not sure. And coronagraphic imaging is, and I'll show an example of that a little later on, is a way to try to directly image extrasolar planets, which is very difficult to do. And if you can directly image them, you might be able to do spectroscopy on what you see. And the GRISM spectroscopy combines a prism and a diffraction grating so that you don't actually have a slit. So all the spectroscopy on the James Webb Space Telescope is slitless spectroscopy using a grating combined with a prism. You have quite a bit of capability here. This is the near spec instrument. It shows the limiting sensitivity in nanojanskis. Well, the Jansky, a typical radio astronomy unit, I put down here, is 10 to the minus 26 watts per square meter per hertz of bandwidth. So it's a flux measurement. So 10 to the minus 26 is a really tiny number. 10 to the minus 26 watts is a really tiny number. And this sensitivity is in billionths of that. And so as you can see, they're sensitive to pretty low numbers. Down at the low wavelengths, their sensitivity is not very good. But as you go up in wavelength, the sensitivity gets much better, say 2 to 4 microns. And then going out to 5 microns, it tends to lose sensitivity again. So this device has what's called an integral field spectroscopy, where you have like a mirror with multiple facets that reflects light into multiple spectrometers. And it has a very peculiar micro shutter array. So you may be familiar with the fact that large survey telescopes, they will mask the telescope aperture and with a mask that has holes drilled in it that match a pattern on the sky that you want to look at. And you point your telescope and you have fiber optics connected to each one of those things. I think Jeff Schroeder actually worked on some of that stuff. And so you can do spectroscopy on all the objects that you have masked at once. Well, on the ground, you can take one mask off and put another mask on. In space, you can't do that. And so there's a shutter array, a window that covers the instrument that has automatic shutters on them that open and close. And those shutters are like a micron, a couple of microns across. They're micron size shutters, very tiny, and they can be controlled by the computer. So if you know what part of the sky you're looking at, you can open up the shutters you want and get multi-object spectroscopy and multiple object imaging the way you would with a masked telescope on the ground. And the near infrared imager and slitless spectrograph, which has imaging, wide field grism and single object grism and aperture masking, interferometries, all kinds of capabilities. Exactly what the scientific application of each one of those is, I just wrote this talk and haven't been able to figure that part out yet without reading a lot more of their documentation. This one, again, you can see at the shorter wavelengths, their sensitivity is not that good, but it gets really good from about 1.2 microns. And even though the plot doesn't go out to 5 microns, it's flat out that far. So it's pretty much the same from like 1.3 all the way out to 5 microns for sensitivity. So you're looking down around 1 times 10 to the minus 20 watts per square meter. And so this instrument is sensitive only to brighter sources than some of the other instruments because they were down to 10 to the minus 26. Well, that was a bandwidth issue. And here are the filters for the mid-infrared MIRI instrument. So the imaging filters are on top and the spectroscopic filters are on the bottom. And it comes in, I guess it's 4 channels. The exact capabilities, I'm not sure if you can only do spectroscopy 1 channel at a time or can you do multiple channels at once. But anyway, you have spectroscopic capabilities that go out to nearly 30 microns. And the idea is that the James Webb is supposed to see out to a redshift of at least 20. John Mather says he thinks it can see out to redshift 30, but certainly it will see to redshift 20. The most distant object seen by the Hubble Space Telescope yet is a redshift about 10. And so redshift 20 should, in theory, get you to the place where you can actually see the first galaxies being formed. And I'll go into that a little bit more in a minute. And so I remind you that here's the comparison between the James Webb mirror and the Hubble mirror. And remember that the Spitzer mirror was much tinier, like the little hole in the middle of the Hubble mirror, basically. And of course, this James Webb mirror is gold, which is much more efficient at reflecting long wavelength infrared than either silver or aluminum, which is why both Spitzer and James Webb are gold. Any long wavelength instrument, the reflective coating will be gold instead of aluminum or silver. So because the mirror is so much bigger, you should get much higher resolution. But of course, this telescope hasn't launched yet. We haven't looked at anything yet, so we don't really know what anything's going to look like in it yet. So this image shows you the Hubble Ultra Deep Field. So in the upper left is just a straight image of the Hubble Ultra Deep Field, and they're zeroed in on that blue galaxy. And that's what it looks like in the upper right in the HUDF image. That's what it looks like to the Hubble Space Telescope. So what we do is take this image and deconvolve it by removing the point spread function of the Hubble Space Telescope, and then reconvolve what should be an image of the sky with the James Webb Space Telescope point spread function, and it's a much bigger telescope, so it has a much narrower PSF, and then you get the field reproduced on the lower left and that object on the lower right. So if you compare the two right-hand images, you're seeing what should be a valid comparison between the image resolution you'd get on the Hubble Space Telescope in the upper right and the James Webb Space Telescope in the lower right, looking at the same object in the same field. You see, not only do you see a lot more detail in the galaxy, but you see a lot more objects in the background. And when I worked on the Spitzer Space Telescope, deconvolving the images like this is one of the things that I played around with. And so what we discovered was that when you artificially enhance the resolution with a narrower point spread function, you bring objects that are so low in intensity in the original image that it's hard to distinguish them from noise. You can bring them up, and you see in this image a lot of objects in the lower right that are not visible in the upper right, because you're pulling them out of the noise, the confusion noise, as we like to call it. But when you do that kind of a trick, you can create sources that don't exist. And we knew that. And so we tested our software on artificial images that we created, so that we knew what every object in the image was, and then ran it and many times to make sure we never created any fake images, and we didn't. And so I think this is a valid way to look at the image. It's highly unlikely that this will create false images, or the way we did it with Spitzer would have, and it didn't. So this is what the resolution difference is going to look like. So with that in mind, this slide, see that James Webb Space Telescope people have spent like $10 billion, but they're too cheap to make their own image. So they just swipe this from the Hubble Space Telescope and put it on their web pages. Hence, the James Webb Space Telescope is in the future, which it has been for a long time and still is today, because December 18th is in the future. But with the Hubble, ultra deep field, we can see down to about a redshift of 10. Actually, I think 11 is the current record holder, which gives you a universe. It lets you look at the universe as it was about a little bit more than 400 million years after the Big Bang, maybe 450 million years. And what we find when we do that is that galaxies have already formed. We're not seeing the formation of the first galaxies or the first stars. That part's already done. And in fact, even looking back at the universe only 400 million years after the Bang, you can see a few fairly large galaxies, which is kind of peculiar. You would have expected galaxies are simply kind of small, given our understanding of how galaxies form. So we can say that we know the first galaxies and the first stars formed earlier than we expected. So if you can see out to a redshift of 20 with the James Webb Space Telescope, which is why the wavelength range goes out to nearly 30 microns, so you can see that far, and maybe the wavelength to redshift 30, you can see what the universe looks like maybe 200 million years after the Big Bang. So what we're hoping is that we will see the creation of the first stars and first galaxies. The James Webb Space Telescope people say they will see that. That's what the Hubble Space Telescope people said, and they didn't. We don't actually know when it happened, but we're getting a little bit worried because it's actually happening pretty fast, faster than we kind of know how to make it happen. And so if the James Webb Space Telescope still can't look back far enough to see the formation of the first galaxies and the first stars. And we have to go back to the drawing board on our theories of how these things form, because that's just not enough time. 200 million years after the bang is you're really running short on time to do that kind of stuff. So even if it doesn't see that, it will be very informative, whatever it does see. So there are 4 major science objectives to the JWST. The early universe, that's to see the formation of the first stars and galaxies, so you can figure out how it happened. Look at the evolution of galaxies and the galaxies over time theme. There's a star life cycle theme, which is looking at star formation and stellar evolution. And the other worlds theme, extrasolar planets, because everybody's always looking for life in the universe. And that's if you can figure out a way to look for life somewhere, it's great. Everybody wants to look for water all over the place. And I like to remind people that you can in fact see molecular water in sunspot spectra. So there is water on the sun, and we're not looking there for life. So just because you can see water doesn't necessarily mean that you can look there for life. But people will be looking for water, oxygen, a whole bunch of other things. This slide is one of our one slide fits all history of the universe slide. You see the Big Bang. About 400,000 years after the bang, what happens is that the original plasma cools off enough that electrons can bind themselves to protons and form hydrogen. So when it says the recombination occurs, what it's talking about is electrons recombining, if you will, with protons. I don't think they were ever combined in the first place. So why they call it recombining is not clear to me, because you have to have done it before to redo it, and that never happened. But anyway, that is where you generate the cosmic microwave background, because at that point, the radiation and the matter decouple, and the radiation sails through space without strongly interacting with the matter anymore. And that happens at a redshift of about 1100. And then there's this little period called the Dark Ages, in which there is no light. And then when things get hot enough, structure starts to form, you ionize some gas and you start generating stuff that you could call visible light. And you have this reionization epoch. In this case, that actually is because back after the Big Bang, everything is solid, completely ionized. It's plasma, and then it becomes neutral, and then it begin to reionize again. And somewhere in here, you start forming the first stars and the first galaxies, probably a few 100 million years after the bang, around a redshift of 20 or 30. And so it's important to remember that the redshift tells you how far shifted over in your spectrum the spectral absorption lines are, and the difference between this, which is around redshift 20, and this, which is redshift 1100, is observationally huge, and this is not linear at all. So to build an instrument that can see to redshift 40 or 50 is going to be a real challenge. And we can see 1100 because we see the cosmic microwave background, but how do you pick up the stuff in between is going to be a real challenge if we don't see what we want to see with the James Webb. So this is actually a movie. So we're going to fly through the cosmic web, which is the first structure, as far as I can tell, in theory, that forms after the bang. It's the dark matter collapses and the baryonic matter collapses, and you wind up with this filament structure, and we'll fly through it just so you can see what it looks like, so that the universe is filaments and voids. Its matter and energy are not evenly distributed. And to form this kind of structure, you have to have an expanding universe. There's the thermodynamics, stuff cools. And if you run a model like this without an expanding universe, you don't get any filamentary structure. And this is another pirated Hubble Space Telescope movie. So this was showing you how Hubble can look at the filamentary structure. This looks like a black slide. It's not. There's actually a movie that will play. But one of the things that JWST is supposed to do is look at the formation of the first galaxies. And so this is a movie showing how we think the first galaxies form in the context of the cosmic web that we just saw. So this is a short movie that, so you see the filaments of the cosmic web and stuff begins to fall into it. So we think galaxies formed hierarchically. So the bigger galaxies suck in the material around them. And as they get bigger, their gravity goes up so they can suck more stuff in because they got more gravity. And this is a video image of how we think galaxies actually form. So ideally, what you should see, and I'll play that one again, actually. Ideally, what you should see, since we can't see a movie like this with any telescope, what you should see is as you look farther back in time, the population of galaxies should be increasingly dominated by small mini galaxies that are colliding to form the big galaxies. As I said earlier, we're looking at the universe when it's 400 million years old. We already see some of these big galaxies. So this has already had a chance to happen. So when does it actually happen? You want to look back and see evidence of this kind of conglomeration going on. And so here is it goes along with the evolution of galaxies science theme that kind of ties in with the formation. This is the Hubble Ultra Deep Field again, and these are all Hubble images. And when we look at galaxies, we're used to looking at these really great pictures of the Whirlpool galaxy and M31 and M100 and great grand large spiral galaxies. Everybody loves to look at images like that. But cosmologists look at galaxies and they look at smudges like this. Smudge is what you get. The galaxies that cosmologists look at are dominated by things that look like this and look like this. They look like anything. Look at this. What's that? How do you know that's a galaxy? From the spectrum, you have to look at the spectrum. And so the Hubble Ultra Deep Field has a lot of these things in it that we recognize as galaxies, and one of them that we looked at a little while ago. But throughout this background image, you see lots of little things floating around out there, all galaxies. There's only one or two stars in the image. And so there's an array of galaxies over here on the right in their little windows that show you the red things are high redshift distant galaxies and relatively small. So when we look with the Hubble Space Telescope, we do see that the population of galaxies is increasingly dominated by smaller galaxies. And I think my next image actually shows that. Yeah. So you can see that up on the upper image here. Whereas we look farther back in time, farther back in redshift, the morphology of the galaxies is different. It's less well ordered, it's more irregular, and the galaxies are smaller. So we see this progression looking backwards already in galaxy morphology and size that is consistent with the model you saw of galaxies forming hierarchically. But you want to get an image, like a still picture of something like that happening, where you got the big galaxy and the little galaxies kind of falling into it. You want to see that to calibrate the beginning of when did it actually happen. It was long thought that, well, back when I started at JPL in the 1980s, people thought, oh, well, galaxies didn't form until like 1 billion years after the Big Bang. And now we know that's complete rubbish. Now we know that 400 million years after the Big Bang, you already have big galaxies. So galaxies form a lot faster than we thought that they would. one of the themes, science themes, is to star formation. Well, the Hubble Space Telescope has told us a lot about that. And these are all images on the lower left. This is a whole collection of the proplyds from the in the Orion, in the near the M42, the Orion Nebula, stars forming that have their little cocoons, where a wind from the star forming blows out a little bubble in the environment around them, and they're called proplyds. And they come in all kinds of different sizes. They look like tadpoles, they look like hamburgers, they look like all kinds of things. And up on the upper right, some stars forming, and especially things like this in the middle, DG Tau B. The dark band in the middle is an accretion disk. So we're looking edge on at a disk around the forming star. And because of the way the magnetic field wraps up into plasma as the star forms, you expect and do see axial jets flowing out. And that's what you see here. You see the jet and light reflected off of dust around it. So the Hubble Space Telescope images are able to show us that stars form the way we thought they did. It's the theory and the Hubble images are nicely coincident with each other. For the James Webb Space Telescope, because of its much higher resolution and its ability to look at higher redshift, hopefully you can see the very first generation of pure hydrogen stars form. And looking at things like this, you can see in much more detail the microphysics compared to Hubble images of what's going on, to help you suss out what's the role of magnetic fields, what's the role of angular momentum of the accretion disk, all these things that are still questions. And one of the projects I worked on with the Spitzer Space Telescope looked at opening angles for things like this, where you see there's an angle here and there's an angle here. And we realized that there's an age correlation where the wider the angle, the older the protostar is, from as best we could tell with Spitzer images. But we could look in longer wavelengths than Hubble could. And James Webb will do the same thing. So James Webb will be able to duplicate a lot of the star formation imagery that Spitzer did, but with much higher resolution. I also want to look at extrasolar planets. There's a couple of ways to do that. One is through spectroscopy. And I was really surprised at how quickly scientists were able to begin studying the atmospheres of extrasolar planets after they were discovered. So in the visible, like what the Hubble Space Telescope does, you need to have the extrasolar planet over here in front of the star. And when you do that, the starlight shines through the atmosphere of the planet. And so you get a spectrum like this of star plus planet. And then you wait for the planet to go behind the star when it's transiting. And now you have only the star, and you have the spectrum of the star. Well, if you have the spectrum of star plus planet minus the star, you get planet. And this is the key to doing spectroscopy of planetary atmosphere. In the infrared, you can do it like this when you're not transiting, but the situation, the contrast is much more favorable in the infrared to see the two of them together. And then instead of looking at the absorption spectrum of the atmosphere, you're looking at the thermal emission from the atmosphere. So absorption and emission. So this would be, in this case, would be an emission spectrum. And so in the infrared, you can theoretically see both an absorption spectrum and an emission spectrum, and begin to work out what's going on with the planetary atmospheres. We can already do that a lot from the ground, and with Hubble. From James Webb, you'll be able to do that with extrasolar planets farther away, and of course at much higher resolution, spatial resolution and spectral resolution, to give you a good idea of what's going on with extrasolar planets. And the other one I talked about, this is an animated GIF. You can see the year and date on the lower left corner. So this is a movie of the triple or quadruple planet system going around HR 8799, it's a K-class star about 133 light years away. And I can't read the apparent magnitude, but I think it's pretty close to eyeball magnitude. But it's in Pegasus, so it's observable from here whenever Pegasus is, so you can actually look at it in your own telescope. You won't see the planets no matter how hard you try. So this is a coronagraphic image. I remember I mentioned one of the instruments had coronagraphic imaging capability, and the central star is here, but there is a disk, a coronagraph that simply blocks it out. And when you block out the starlight, then you can see the planet. If the star were actually here, you'd never see the planets because the contrast is so crazy that they're wiped out and you'd never see them. So you need to get rid of the star. You can try to do that by subtracting the star in a deconvolution, but you still have a lot of noise around it, and that's a very difficult thing to do. But it's much easier and much more reliable to just put a black disk up in front of the telescope and block out the starlight altogether, and then you'll need to worry about it. So you just have this funny stuff going on in here, and then these images of the planets are reasonably reliable. So with coronagraphic imaging, you can actually do direct imaging of extrasolar planets. And if you can, you should be able to do slitless spectroscopy on these things and get their emission spectra. And again, tells you something about the planetary atmosphere. Well, that's the end of my regular slides. I'm going to try to run the YouTube video here because my last slide, when I did this before, you should be able to, there's sound with this, but it's just background music. I don't know whether you'll hear it or not, but you don't need to hear it because nobody's saying anything intelligent or interesting. It's just background music. You should see the my web browser come up and play the movie. If you don't see that, tell me, and I'll try to change the way I share my screen. The movie's about 5 minutes long. It comes from Northrop Grumman, and it details in excruciating step by step exactly how the James Webb Space Telescope unpacks itself in flight. So can you see my web browser? Can you see my image?
No, I don't see the image.
Can you see the movie?
No, I'm going to write down that.
I hope you
and we'll
can.
put it.
So of course, if the solar array doesn't deploy, then of course it's hopeless.
All right.
Tim, we aren't seeing it at all. At all.
I'm going to go ahead and stop the recording at the moment.